Okay, so do you see that? Okay. So I want to start teaching, hopefully. So we, in this course, dealing with very important topics, dynamics. Dynamics. Can you hear me well, and can you see the screen? Anyone?
Yes.
Okay. So, as its name implies, dynamics versus statics that you had previously. Statics. This is dealing with the systems that have no velocity. Velocity is 0, and the acceleration is 0 in the static course. But when it comes to dynamics, you do have velocity, non-zero, and you have acceleration, probably. If the velocity is changing, like a car that you're driving every day toward university or back home, you're gonna have dynamical system. Name it from, I don't know, say from cars to satellites to robots to turning satellite in your home, a satellite dish, whatever, and yourself as a dynamical system when you're running, when you're moving, whatever it is that is changing with time, changing with time, changing with time has a dynamics. This is simple definition of dynamics. So you tell me, what's the mathematical expression for changing with time? What is changing with time definition in mathematics? You tell me, you help me, because I want that you participate in class.
Derivative?
Yes, means derivative, d over dt, means changing with time. Because this equals with delta, remember from kindergarten mathematics or pre-kindergarten, or delta over delta t. Delta means changes. So right? When delta t goes to 0, gives you derivative. That's right. When you are decreasing the time interval, gives you derivative. Now let us play with this term, derivative or differentiation. If you want to explain derivative to a 5-year-old kid, or even smaller than that, that they have no background of mathematics, or they have nothing about, they don't know nothing about the dynamics, statics, algebra, how you explain the derivative to a 5-year-old kid? Simply, by one word. Only one word. I want to examine your ability to easily understand the topics. Because Albert Einstein said, if you cannot explain anything to a child, it means that you didn't understand. You pretend that you understand that topic. In one word, explain to me what the meaning. What?
The shower wasn't draining right, yeah.
What? Please mute your mute your microphone, guys.
So it's fine now? Thank you.
Guys, I don't care that your shower is not working.
No bottom.
Please mute your microphone.
Thank you.
Please mute your microphone.
It's Kelton, by the way. So Kelton. Sorry.
You are talking about shower, okay? So, in one word, explain to me what's the meaning of derivative, time derivative, or any derivative. Anyone? Brainstorming?
Change.
What? Again?
Change.
I know, but change, okay. You're gonna say change to 5 years old? Everybody knows that
no,
means
I'm
change.
not. Maybe
Mark Osorio in chat, he said slope.
You are one step closer, but slope has no meaning also for a 5 years old kid.
Respect.
What?
Respect.
No.
Okay.
Okay, guys, it's interesting. I think that all of you passed the trivial algebra, that's right, in high school, at least. Even not in the university, but in the high school. If it's a function of time, this is f of t, a function of time, and this is time. You have things like derivative, integration, right? Yes? So mathematically, we know that integration means what in this graph? Means area under this graph. Exactly. This is integration. Bingo. And we know derivative, as your friend said, let me change the color. At this point, derivative is the slope. That's right. Yes? Yes, everyone? At point t naught, a given point, at point t naught. Yes? Now I use your beautiful eyes and put down here, huh? I put your eyes, this is your eyes, huh? With the eye, with this. And you're looking at this point by your eyes. What do you see? This is your eye. What do you see from that point? This is going up, that's right, this is slope. What do you see?
A line tangent.
I know, this is mathematics still.
A function.
No. You see the future. You see the future, that's right? Huh? You see how this curve will behave after this. Clear? Huh? So one word for differentiation means that you're gonna see in the control class with me in 500 level class or 600 level class. Derivative simply means future. You are seeing the future of a function. Okay? Now, if I say between t1 to t2, integral means the area under the curve from this point, what do you see? What do you see for integral? Looking at the back, what do you see? This is future.
Past.
Yes. Integration simply means past of a function. I'm not kidding, I'm serious. When you want to try to explain to a 5 years old kid, oh, I'm dealing with the integration, means that I'm going to dealing with the future. Okay? I'm dealing with the integration, I'm dealing with the past. When you pass the control course with me or another professor here, we have also present time. I cannot explain right now for you because this is out of the scope of this class. But these are simple definitions of the differentiation and integration. And in the dynamic course, if you don't know that you are using differentiation for what and integration for what, you mean that you never understood dynamics. Clear, everyone? Yes? Huh? Okay.
Yeah.
This is basic definitions from kindergarten mathematics, at least in my country. Okay? So, the next fundamentals, before this class, I was teaching the vibration class, ME 520. And I can say that most of the students, they didn't know these topics that I'm teaching right now in dynamic course. Particle, and rigid body. Rigid body. Okay, these two words. If you do not understand what is particle, if you do not understand what is rigid body, you won't understand and you won't solve any problem in dynamics course. I bet. Okay, what is particle? Particle, as name implies, it's a very small amount of particle. This is particle, very small, lumped in a point. And this is a rigid body. Its name is a rigid. The molecules inside that, the distance between them is not changing, it's rigid. But what's the difference between this very small particle and this rigid body? Visually, at least. Visually, what's the difference between them? You name it, simply. Don't go to mathematics.
Size.
What?
The size.
Yeah, exactly. What do you mean by size, technically?
The particle is apart from the rigid body.
Yo, the previous student was right. What do you mean by size, technically? Dimension.
Like area.
Dimension. That's right. Dimension. Particle has no dimension. This is fundamental difference. Please understand this. I have seen master degree in mechanical engineering that I have seen PhD, first year of PhD inside the US that they don't know what's the difference between particle and rigid body. They asked me this question. Okay? So particle has no dimension. Has no, as your friend said, it has no size. But rigid body has dimension. Okay, now the other question is, particle has mass or has no mass? You help me.
It has to have mass, right?
Yeah, has mass. Has mass. What about rigid body? It's very simple.
Yes, also has mass.
Yes, has mass, obviously. So the only difference is, I'm emphasizing a million times, dimension. Okay? So if I want to summarize, particle has no dimension but has mass. Rigid body, RB, I'm writing as rigid body, has both mass and dimension. Now, if I ask you guys, what do you think about our planet? Is a rigid body or is a particle mass?
Depends what it's being compared to.
What? The last one?
Depends what it's being compared to.
What do you mean, that can be both?
I mean, like, the Earth compared to, I don't know, the universe is pretty small.
Exactly.
I guess it depends on your frame of reference.
Exactly. Earth can be particle, can be rigid body. Excellent. Can be particle compared to Milky Way, and it is. But is rigid body with respect to us, with respect to car, with respect to satellite, with respect to the mountain inside. We are talking about a relative dimension. You can assume relative respect to, with respect to what you are talking about. These are fundamentals. If you don't understand, I don't care that you understand the rest of mathematics of this course. Honestly, I don't care. Okay? Because it's like as a tower that has no foundation. I don't care that's a 60 floor foundation, because it's gonna collapse one day, right? So with respect to what we are talking about, dynamics means respect to what? What's the datum that you are talking about? Your car is a rigid body, respect to your body, respect to yourself. But your car is a particle inside your city. And that's why when you use your GPS in your car, you see your car as a dot that is moving. That's right. So you have to open your mind, you have to open your brain. Don't trap yourself into classical definitions. Nothing is absolute in the science. Nothing. Maybe one day comes that Newton's second law that we're going to deal too many times in this course is being terminated. See what I'm saying? So, again, I'm emphasizing, because it's very important, particle, rigid body. Particle has no dimension, but has mass. Rigid body has mass and has dimension. And when you're judging about the particleness or rigid bodiness of an object, you have to compare with respect to what you are talking about. Until this point, we are clear? Yes?
Yes.
Okay, let's go to the next. Now, in the first half of this class, I mean this whole semester, I'm going to teach you about Newton's second law. And toward the end of this semester, I'm going to teach you the moment equation. So let's go to Mr. Newton. We have famous Newton second law of motion. Okay, as following. As following. So what are those? One. A particle. Now you know what's particle, that's right? All of you, am I right? A particle means has no dimension, remains at rest, or continues to move with uniform velocity if there is no unbounded forces acting on it. This is very obvious. Suppose that you have a particle. Here we go. This is a particle over the ground. If you don't apply any force to that, it's gonna remain at rest. Means its velocity will be zero. Its acceleration will be zero. Okay? Understand? 2. The acceleration of a particle. The acceleration of a particle is proportional to the resultant force acting on it and is in the direction of this force. And I'm pretty sure you have seen this a million times before coming here. Sum of the forces, this means sum, sigma. Sum of the forces, force is a vector, so you have to put a vector sign here, is equal to mass applied by, multiplied by acceleration. So the Newton's second law that you just saw it means this. So the acceleration of a particle is proportional. Proportional means this m, mass of the particle, or rigid body. You're gonna see later. Okay, proportional means this. The resultant force acting on it and is in the direction of this force. This is Newton's second law. 3. The forces of action and reaction between interacting bodies are equal in magnitude but opposite in direction. And co-linear. Guys, can you give me the example of Newton's third law? That we are existing inside that example. Can you hear me, guys?
Yes.
Okay. So did you say you were going to record? Yes, I'm going to record this video. I'm going to put on the YouTube, obviously. I'm such a kind professor. So can you give me the example of the third law of the Newton?
Serving a volleyball.
Yeah, sure, obviously. And I mean a large scale.
Frost.
Our planet and sun. They have attraction, same magnitude, but in the opposite direction. Huh? Yes or no? Yes or no, guys? This is valid for this? Think about this, guys. Is this valid for this? But another, as you said, it's volleyball. When you're hitting the ball, in the contact point, it's the same force but in the opposite direction. Or when you, by your hand, push a table, paper is gonna push you up. That's right. What about this, guys? Is this valid? Think about this as homework for yourself. Sun and planet. So, yeah, go ahead.
I was just saying that I think it's valid.
Okay. What's the reason? What's that?
Because the gravitational pull on the sun on planet Earth is going to be pulling it in, but then planet Earth is going to have an equal and opposite reaction on the sun. Only keeping it where it is.
Okay. Good. So all things that we are talking about in dynamics course, okay, we have to measure with respect to I'm changing the color because very important, a reference or datum system having coordination. So first that you have to do, like as statics and dynamics, the very trivial and immediate step that you have to take to solve a problem is that you have to set up your coordinate system. You may say, I know it. That's the most biggest mistake that you can do as an engineer. I know it means that you're going to make mistake $10 million bet from now. There is no I know it in engineering. You have to go step by step. The first step, when you're dealing with the dynamics, vibration, you have to set up your coordinate system. You have to. Don't imagine it on your mind. Okay? Like what? Like such as attached to the surface of the earth. Okay, so this is our earth and the continent like this. When you are talking about this, first you have to set up your coordinate system. X, Y, Z. If you don't do that, you are done. You're gonna make mistake. You're gonna apply Newton's second law in a wrong way. I bet. Okay, guys. Another fundamental question I have from you guys is, why are we name it as X, Y, Z? Why we write as X, Y, Z? Why we are not saying as X, Z, Y?
Convention.
What convention?
Math convention.
The convention has a name.
Is it a right-hand rule?
Yes. A right-hand rule. Right-hand rule. That's right. So the person that said right-hand rule, what's the right-hand rule?
So it's essentially where you have your thumb along the z-axis,
Right.
and the z-axis is vertical.
Yes.
And it's essentially used for, I think it's moments where it's more of a visual thing, but you essentially have
Okay, if you put your thumb at the Z, from X, the other four fingers, when you're rotating to the Y,
exactly, yeah.
your thumb must show Z. When you put your X, Y, Z, that's right. When you put your thumb on the X, the four other fingers must show rotation from Y to Z. That's right.
Yeah.
And when you put your thumb on the direction of the Y, the other four fingers must show from Z to X. So that's why we say X, Y, Z. See, X rotation, this rotation, this rotation. Clear to everyone? This is not by accident. This is a role in the engineered system. Everyone clear? Rotation is like this, X, Y, Z. This direction, this direction. You cannot say xzy. Okay? Understand? Okay, so these are very trivial but important. Now, as your friend talked about, now we know these trivial but very important definitions. Let's go to gravitation. Gravitation. Gravitation principle states that the mutual, that Newton's third law, that's right, mutual attraction. The example of sun and the planet that I gave you to give you brainstorming, it was because of this gravitation. The mutual attraction between bodies, is as follows. F equals to G. I don't know what happened to this thing. Is gravitation between my hand and the screen. M1 M2 divided by R square. We have two bodies, mass of M1. So let me break it down for you. So okay, F is the mutual force of attraction, like between planet and our sun, between two bodies. G is a universal constant called what? The constant of gravitation. Constant of gravitation. Okay? M1 and M2 are the masses of the two particles, and R, this R, is the distance between the centers of the particles. Okay? And the G value is measured as 6.673 multiplied by 10 to the power of minus 11 meter cube divided by kilogram multiplied by second square. Understand? Now, before going to an example, let me give you the last topic in the gravitation, which is effect of altitude on the gravitation. Altitude. altitude. It's interesting to know that if you put 1 kilogram mass on the surface of our planet, the gravitation is 9.825 Newton, as you know. If you put the same mass, 1 kilogram, 1 kilometer above the surface of our planet, the gravity is 9.822 Newton. You see, it's decreasing. If you go higher, this 1 kilogram in the 100 kilometers, the gravitation decreases to 9.52 Newton. If you go the same 1 kilogram, if you go to 1,000 kilometer, it was 7.34 Newton. And if you go 1 kilogram to 6,371 kilometer above the surface of our planet, gravity goes to 2.456 Newton. And you heard that we have the vacuum conditions, right? When there is no gravity. If you go much higher, gravity is almost zero. So altitude has an inverse relationship with the gravity. Now suppose you have a mass here, particle mass, on the surface of our planet. Based on the gravity, and Newton's third law, there is an action and a reaction between these two things. So let me plot the free body diagram. This gonna apply here. M1g, gravity acting on this, and this is gravitational force. Gravitational force gonna be G M1 M2 over R squared with respect to the center of our planet. This is center of our planet. So here is R, the radius of our planet. That's right. So they are in the equilibrium. So M1G. Why they are in the equilibrium, guys? Why they are in the equilibrium? Come on. The radius of our planet. Anyone? Why these are equal?
Newton's second law?
Yes. What do you mean?
Equal and opposite reactions.
And what is Newton's second law? Look at here. F is equal to ma. So if we have acceleration here, this is gonna move. That's right, this particle. Yes, but it's stationary on the planet. Look at yourself. You are just sitting and there is no motion, right? So this is zero. So the forces are in the equilibrium. So that's why they are equal. That's right. Yes. You see what I'm saying? Yes, guys. So by doing that, this goes to New York. Only the mass of the Earth, this is E, mass of Earth is important. By having the numbers, mass of the Earth is 5.976 multiplied by 10 to the power of 24 kilogram, measured by me, and G is 6.371, as I told you previously, 10 to the power of 10 to the power of minus 11. I'm sorry, guys. Okay. And the radius of Earth. Okay. So you can calculate from here that the gravity of the surface of our planet, as we know, is 9.825 meter per second square. Bingo. That's right. Yes. So this is how we calculate the G, gravity, acceleration, gravity. Okay, gravity, acceleration. Now, if you use that formula that I gave you previously, okay, you can say at the altitude h from sea level, gravity, okay, sea level, say gravity at sea level is G naught, means 9.8 that we calculated. The new G at altitude h, or G of h, equals to G naught, radius of our planet, and plus h square. This is how we calculate the gravity. Clear? Yes?
Yes.
Great. Now let's go to the problem. So one example. Problem. Okay? Suppose you have two particles. Okay? One of them has a radius of the r, another has radius of the 2r. Okay? And there is a gravitation between them. And the angle between these and the horizontal line is 30 degrees. Do we have anyone that is calling me? No. Okay. Okay. And the distance between the center of these, the centers, okay, these are two spheres, okay, is the centers. Oh. Is 8r. Okay. I want that to calculate the gravity of the higher sphere, that is because there's gravity between them, okay? And the given information is r is equal to 5 centimeter, okay? 5 centimeter. And these are the spheres, iron sphere, so these are iron spheres, okay? Iron spheres. So I give you just a few minutes that you calculate for yourself, then I'm going to solve this problem.
Both are from iron, right? Same.
Yeah, they are iron and they are spheres. Calculate F in x direction, this gravitation force between them, and Fy, calculate these for me. So because obviously the bigger mass, bigger object attracts the other object, that's right? Yeah, so that's why this is downward. Let me say this is mass A, this is mass B. Sphere A, sphere B. Okay, the solution is very easy. So what you're gonna do, you're gonna say F gravitational force is G MA multiplied by MB and the distance between them. First you have to calculate M. You know from physics of high school, M is density in volume. That's right. So because these are spheres, the volume of a sphere is 4 divided by 3 multiplied by pi in r, radius of that sphere cube. You can find it in Google even. Okay. So because this is iron, so density of the iron is 2700 kilogram per meter square. So multiplied by 4 by 3 in pi multiplied by radius of the particles cube. So from here you can have MA, mass of A, is 4 multiplied by 2700 multiplied by pi divided by 3. So radius of the MA, this is A, right? 2R. R is 5, so 10 centimeter. So gonna be multiplied by, you have to convert it to the SI system, to meters second. So it's gonna be 10 centimeters. So it's gonna be this meter cube. Okay, 10 centimeter is gonna be 0.1 meter. So if you calculate that, you get 11.13 kilogram. MB, the smaller, is the same, multiplied by pi divided by 3. Its R is 1R, 5 centimeter. So convert it to meter, gonna be 0.05 cube. This is 2R, this is R. If you calculate that, gonna be 0.41 kilogram. So you have this, you have this. You also have this radius distance between the center of both bodies. How much is that? Centers, 8R. So F is G. We have G already. 6.673 multiplied by 10 to the power of minus 11 multiplied by MA, 11.13 multiplied by MB, 1.41 divided by R is 8R, 8 multiplied by 0.05 square. Okay, clear? So the result is, if I have the numbers, is 664.53 multiplied by 10 to the power of minus 11 Newton, because the force unit is Newton in SI system. Until this point, clear? Yes? Guys? Can you hear me?
Yeah.
Okay. Now, but we want fx and fy. I told you you have to set up your coordinate system first. So let's do that together. So here is x, here is y. So this is the same force, that's right, F. So your F, you have to decompose it. Here is 30 again, because here is 30. So you have two components, Fx, Fy. That's right, this is vector. Here is positive, here is positive. That's why you have to set up your datum, your coordinate system, your origin, to know where is positive, to know where is negative. So here is negative, here is negative. So your Fx gonna be F from trigonometry, cosine 30 degree. Here is gonna be F sine 30 degree. Everybody knows this from trigonometry? Yes? Yes, everyone?
Yep.
Okay. So, let me see. Yes, okay. So, your f as problem 1's vector gonna be minus f cosine 30 in I direction minus f sine 30 in J direction. Yeah.
I'm sorry, I have a question.
Sure.
Can we go back to the previous slide?
Sure.
Isn't it should be like a tension force, not like
Tension? What's tension?
I mean like the gravity, the attraction.
No, it is attraction because this is greater than this, so it's attracting the other smaller particle. This is attracting that. That's right. It's pulling towards. Yeah.
So the big.
Always sun is attracting the planet, right? Sun is attracting moon. Sun is attracting Mars. Sun is attracting. So it's pulling this particle toward itself. It's pulling this way.
So the direction of like the vector f in the right direction, like this, right?
Yeah, this is
Okay.
Yeah. If I draw like this, means that the smaller attracting the bigger.
I expected that it's going to be like equal forces, equal attraction.
That's
forces.
why I asked that question at the beginning. Remember sun and planet? And I asked that, is it right? Okay?
Okay.
See?
But I believe, so maybe I'm wrong, but I think the Earth is affecting the sun with the same amount of attraction force that the sun affecting the Earth. Am I right or wrong?
You are right, but they are at equilibrium. We are talking about this force now, okay? Attracting our planet, okay? Understand what I'm talking about? Okay.
Okay, got it. Thank you.
Yeah. Okay. So, if you plug the numbers, okay? If you plug the numbers, so F is minus 3.32I minus 5.57 J multiplied 10 to the power of minus 9 Newton. Okay? Understand? So that's it. So based on the Newton's third law, there are at the same amount but in the opposite direction. Clear? Okay. So I'm going to stop it here, and next class I'm going to start about teaching kinematics and kinetics. Okay, that these are other very important trivial and basic ideas in the dynamics course. Okay, clear? I think that what was your name? You asked the question, please. I think you confuse between this where it's placed. That's right, sir.
Me?
Yeah. This means it doesn't mean affect this. This force affect this small amount, not itself. We are just transferring to show it. Okay? Understand what I'm talking about? Yeah. I think that because of the place you thought that this is doing this. No, this is attracting the smaller particle. Okay? Understand? So That's it. Any other questions for today?
Wait, sorry, Professor, I had a really quick question. Where can we find the recordings of lectures for future reference?
It's being recorded right now, and every class I'm gonna send to all of you by email. It's a link I'm gonna put on the YouTube.
Okay, thank you so much.
Yeah, sure. Okay, so let me stop this because it's gonna be very